Oh, yeah. Okay, so for polynomials, and it's not just polynomials, but for single functions that don't have quotients, okay? But the ones we did were polynomials. If you replace x with negative x, and you simplify all the way through, then if none of the signs change, if they all stay the same, then the function is what? Even. Yeah, even. There we go. Which means it has y-axis symmetry. If all of the signs change, then the function is odd, right? Odd, all. They kind of sound the same. And if some change and some don't change, then it is neither, neither. Yeah, neither, neither. All right, and then for quotients, which is how we're going to be doing it in the future, we're not going to actually do that formal proof like we did on the quiz. We're just going to be able to determine by glancing at it. So if you have a quotient of two even functions, then what? An even divided by an even is what? Even. I'm just going to use E for even. There we go. And if you have a quotient of an even and an odd function in any order, then of course it's what? Odd. If you have a quotient of two odds, even. Good, because odds act like negative numbers and even functions act like positive numbers. Good. And then if you have a neither over a whatever, or a whatever over a neither, where whatever could actually be even, odd, or neither, right? Then it's what? It's neither. You don't invite neithers to your party if you want to keep it going, right? There you go. So it helps to have these rules memorized so that you can eventually, without doing all this analysis, you could just look at it and determine if it's even, odd, or neither, okay? Putting it all together now, example 7, okay? This is going to be kind of a glorious review of pretty much everything we've talked about so far this year. For each of the following, find the domain, the end behavior, the X-Intercepts, the Y-Intercepts, any symmetry, and label all discontinuities. Use your collected information to sketch a graph. Oh boy, oh boy, oh boy. Okay, here we go. Whew. What type of function are we staring at here? What? It's a quotient of two polynomials, so we call that it's a ratio of two polynomials, so we call it a rational function, right? Rational function. Okay, what should we do first? I mean, we're ultimately trying to sketch the graph. What should we do first? What was the first thing that we ever did? Find the, what? Oh, we could do that first. Yeah, I mean, the order doesn't really matter. When you find the biggest exponent, you're looking for end behavior. We could do that. I'm going to hold off and do that second, actually, okay? Because the first thing you want to get in the habit of doing when you walk into a function after you introduce yourself is find the domain, okay? That was kind of the first property that we looked at. We find the domain. Now, when we did it, we went off to the side and we set the denominator not equal to 0. And you can still do it that way. That's fine. But we have another way now that's a little bit more efficient. If we can simply factor the denominator, we could just use our eyeballs to determine the values that give us division by 0. Because that's the only risk we have here, right? There's no radicals. So let's go ahead and factor it. When we factor it, we're getting a different version of f of x that we're going to be using for different things. All right, what's the first rule of factoring? First rule of factoring is to look for a common factor. Yeah. And in the top, I spy a factor of 2, right? So that gives you x squared minus x minus 2. That makes it easier to factor after that because now the leading coefficient is 1. And in the denominator, I see a 3. So x squared plus 3x minus 10. So notice I called it f of x. If you didn't want to call it f of x, you could have just lined up the equal sign and worked straight down. It's entirely up to you. I'm going to go ahead and bring f of x along each time. So now I can focus on the quadratic trinomials that remain. And so this could factor into the product of two binomials. This could factor into the product of two binomials. So in the top, I got factors of -2 that add up to -1. That's -2, +1. And on the bottom, I need factors of -10 that add up to +3. What are they? What kind of 2 and 5? Yeah, -2, +5. Good, because the sum has to be positive. All right, so should we simplify first and then find the domain, or find the domain and then simplify? Find the domain and then simplify. I'm grading those group quizzes from last week still. It's taken me a while. There were a lot of people that simplified and then found the domain, and we don't do that, right? So right now, we could say the domain of F is the set of all x's such that x is not, and there are two values that make the denominator 0. What are they? 2 and -5, okay? And you can write those in any order if you do it in set builder notation. Of course, if you did it with interval notation, you'd have to go -5 and then 2. All right, so there you go. There's the domain. Now that we have found the domain, we're saying, hey, x can't be these two guys, but the graph can live to the left and right. Therefore, these are types of what? Discontinuities. So naturally, it might be the next thing you want to do. Let's classify the discontinuities. Notice up here then, the x minus 2 factors divide out. They divide out. So I'm going to move this down a little bit, and I'm going to give myself yet another version of f of x. What I'm left with is 2 times x plus 1 all over 3 times x plus 5. But of course, I'm going to remind myself that x cannot equal 2. Now, because the x minus 2's divide out, 2 is still not in the domain. This is where some people, like, they simplify it and they just tell me, hey, x can't equal -5. Well, that's true, but x still cannot equal 2. What type of discontinuity do we have it to? There's a hole, right? If we can remove it, it's removable point discontinuity. If you plugged in the 2 in the beginning, you get 0 over 0. So we'll say f has a hole at. Now, because it's a removable point discontinuity, we always list the point or hole as a ordered pair. Some people are just saying at x equals 2. You're going to lose a check. It's going to be at 2, comma, something. Now, how do we find it? Plug it into what's left. Now, let me give you a word of advice here on notation. If you don't write that x cannot equal 2, I'm not going to take off. But here's what you don't want to do. When you plug a 2 into what's left, you don't want to just say equals, and then you plug in a 2, and you get 3 over 3 times 7, right? Why would you not want to do that? What's wrong with that? Very good. You're saying that the function, which has variables of x in it, is equal to a constant. That's not correct, okay? Because a constant graphs as a horizontal line, and this thing is not a horizontal line. So whenever you use the equal signs, you need to be very, very careful and ask yourself, are the two things that I'm equating actually equal to each other? Because if they're not, you're always going to lose points. So how could you still use that and find the value? It's as simple as not putting an equal sign there. If you just do it somewhere off to the side, that's fine. You're not equating it. In fact, I would do that farther away off to the side, all right? Here's another thing that I've noticed, okay? Let's say that you're not working down. For some reason, you're still heck bent on working sideways. If you have the space to work down, work down. Some people, when they simplify the expression, they'll do it like this. They'll say, okay, right here, that's 2 times x plus 1 all over 3 times x plus 5. If you are working sideways and it is equivalent, now what do you need? Now you do need an equal sign, where a lot of people are just putting spaces between things. So that will also lose points, all right? So if they are equal, keep them equal. If they're not equal, don't equate them. So anyway, I plugged into what was left. I did it off to the side. Notice your 3's divide out, don't they? So instead of calling it 6/21 and then having to simplify, look to divide before we multiply, and we get the wonderful 2/7. Okay, cool. So notice that I'll put this down here. Notice this is not a point on the graph, but it is a place that we could graph. We could graph it with an open circle. All right, what's the other discontinuity now? Vertical asymptote. So F has a VA, you could abbreviate it as a VA, at what? X equals, -5. Good. Okay, so that was kind of the first stuff that we did, right? So it kind of makes sense maybe to find these things in the order that we studied them. Okay, let's go back to Darrow's now. He said to analyze the exponents. I have two versions of my function, really. I have the factored version simplified, and I have the expanded version. When you're looking at the end behavior, it's easier to look at the expanded version, okay? So let's do that. The leading term is 2x squared, and then the leading term in the bottom is 3x squared. So what do you know about the end behavior? They're the same. They're growing at the same rate. So I'm not going to obliterate everything else because I still kind of need it there. But the x squareds would essentially divide out, and I'd be left with what? Leading coefficient over leading coefficient. So let's go ahead and write it this way. The limit as x goes to infinity of f of x is 2/3. And the limit as x goes to negative infinity of f of x also equals 2/3. That's your end behavior analysis. And because those are the same number, you could say, so f has a horizontal asymptote, aha, at y equals 2/3. Okay, now if I didn't ask you to specifically find the end behavior limits, you wouldn't necessarily have to show this. You could go straight to just f as a horizontal asymptote at y equals 2/3. Okay, so symmetry. Let's look at symmetry. For symmetry, it's probably, again, easier to use not the factored version, but the expanded version. So let's just look at that, okay? The numerator. Is the numerator even, odd, or neither? You have an even exponent and an odd exponent. So it's neither, right? So does it really matter what the bottom is now? No, it ruined. The bottom, just for the record, is also neither. What's a neither divided by a neither? It's a neither, right? So I'm not going to show that analysis. I'm just going to say down here, symmetry, none. Okay? It's neither even nor odd. Now that's kind of a bummer. If it had some symmetry, that could help us in our graphing. But maybe the fact that it doesn't have symmetry could also help us in a certain way. We shall see. All right, my ultimate goal is to sketch a graph of this stuff. Do I have enough information so far to sketch a graph, or to start my graph at least? Yes, we do. So let's come over here and let's create a nice little axis. Y-axis, snap, there we go. And x-axis, snap, there we go. All right, so the first thing that you should get in the habit of sketching, I'll put this up here, you want to sketch your asymptotes first. Okay, just as a rule of thumb, sketch your asymptotes first. Why? What's that? Yeah, so you know where you can't pass. They kind of define 4 new quadrants. If you have a horizontal and a vertical, they kind of define 4 new quadrants. Plus, remember, they act like black holes. The graph is just irresistibly drawn towards it, so you can kind of see where we're supposed to be tending towards. So let's do that first. We have a vertical asymptote at -5. So I'll just kind of go 1, 2, 3, oops. This doesn't look good. 3, 4, 5. And I'll label that as -5. And then I'll just put a dotted or a dashed line. Whatever you want. There it is. And then we also had a horizontal asymptote at 2/3. So I'm just going to come up here, and I'm just going to label that 2/3. So your x and y axis don't have to be scaled the same. And I'm just going to put a dotted line all the way through 2/3, something like that. Guidelines, all right? So notice the intersection of those two kind of make 4 new quadrants, don't they? 1, 2, 3, 4, right? Sweet. All right, is there anything else that we can plot at this point? There's one more thing we could plot. The whole at 2, 2/7. All right? So 2 is going to be like here, 1, 2. Oh, diggity boy, where is 2/7 in relation to 2/3? Is it above or below? Yeah, it's below, right? So I'm going to just kind of say it's about right here. And we'll label that as 2/7. We're going to get crowded, but then we have an open circle. That's pretty cool. By having an open circle underneath the horizontal asymptote, rational functions, polynomials over polynomials, they don't cross their horizontal asymptotes. So just by knowing that there's a hole here, I kind of already know that the graph lives down here in this new bottom right quadrant, don't I? I mean, it's going to live down here. All right, that's pretty cool. So what else can I find? Well, it talks about X-Intercepts and Y-Intercepts. That's old school stuff from Algebra 2. Let's review that. Let's find Y-Intercepts first. I think they're the easier of the two. In general, how do you find a Y-Intercept? A Y-intercept is a point on the Y-axis. What coordinate do you know on the Y-axis? The X or the Y coordinate? If you have a point on the Y-axis, that coordinate is going to be, what's the X coordinate? 0, right? If you're on the Y-axis, you're at X equals 0, aren't you? So how do you find a Y-intercept? You plug in a 0 for X, right? And the way we show that is like this. We say f of 0. That communicates to someone that you're plugging in a 0 for X. Now, you could use any version, but the expanded version is probably the easiest because in the expanded version, what happens to every term that has an X in it when you plug in 0? It turns to 0. It's gone. So you're just left with the quotient of the constants, which is -4 over -30, which simplifies to what? 2 over 15. Sweet. So it crosses at 2/15. All right, so you can also list that as an ordered pair if you want, 0, 2/15. Let's plot that. 0, 2/15. Where's 2/15 going to be? Oh, lower than 2/7. Man, it's getting crowded down here. Crowded. I'm going to move this dot up a little bit. Good thing we have an iPad or an eraser, right? So there's 2/15 right there. I'm going to label that right here as 0, 2/15. It's a popular page. Kind of crowded. No big deal. Now let's find X-intercepts. This one is the one that's generally not as easy, but still just as fun, if not more so. How do we find X-intercepts? On the X-axis, we know one of the two coordinates. Which one? The Y value, right? On the X-axis, the Y value is always 0. So to find X-intercepts, you actually set Y equal to 0, also known as the function. You set the entire function equal to 0. So that's an equation now that we have to solve. Well, because we have a fraction, when is a fraction equal to 0? We have three cases, right? 0 over 0, 0 over non-zero, and non-zero over 0. Which one of those three, let's call this A, B, or C, which one of those is actually equal to 0? B, right? Very good. The first one is a whole. The second one is a what? No, C is equal to what? It's a vertical asymptote, right? 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 I mean, we studied this in Algebra 2. We reviewed it this year. Non-zero over 0 is a type of infinity. 0 over 0 is a whole. So when is a fraction equal to 0? When just the what? The top, when the numerator is 0. Now, if we set the factored version of the numerator equal to 0, before we simplified, we're going to get 2 and -1, making the numerator 0. But is 2 actually an X-intercept? No, because we've already identified it as a whole. So this is where the last version comes in. If I want to find the X-intercepts, I need to know the values that just make the numerator 0. Not the numerator and the denominator, just the numerator. So that's going to be what? You could look at it in factored form. What value of X makes just the numerator 0? Not 1. -1. -1. So up here we'll say f of X equals 0 when X equals -1. So that's how you solve the equation. If you want to write it as an ordered pair, that would be -1, 0. All right? So if it just makes the denominator 0, it's a vertical asymptote. If it just makes the numerator 0, it's an X-intercept. And if it makes both, the top and the bottom 0, it's a whole. Well, we could plot the point -1, 0. It's going to be right there. And what else do we have? I think that's kind of it for now, right? So let's go ahead and see if we can't figure out what this graph looks like. There's a lot of evidence now that this graph is going to live in this new bottom right quadrant. made by the asymptotes. Would you agree? In fact, if you look, the two function values in the whole are kind of lining up. So if you want to go ahead and sketch it, I'll keep purple. It's going to look something like this. You connect those dots, go through the hole, and then just start approaching that horizontal asymptote. You almost draw it kind of parallel to it, right? And then what's going to happen as I continue that graph to the left? It's going to go down, right? Because we got that vertical asymptote. So it kind of looks like our parent function 1 over x, which, not surprisingly, is the parent function to all rational functions. Okay, when the degrees are the same or the bottom's bigger. So that's what it looks like over there. Now, all we have to do is figure out on the left side of the vertical asymptote where it lives, above or below. Gosh, how can we figure that out? Come on, mathematical detectives. You're on a stranded island. Your life depends upon knowing if it lives above or below this horizontal asymptote. At the very least, you could plug in an x value, what? That's smaller than -5. You could just plug and chug, like you did in Algebra 1, right? You made a little t-chart, and you just picked random x values, and you found y values, and you plotted them, and you connected dots. You could plug in any value of x to the left of -5 and see what the y value is, and then connect the dots. But what if I told you there's already enough evidence that we found to determine whether it lives above or below? Would that help you look for it? Okay? Well, it's a true statement. There's already enough evidence that we have found to determine whether it lives above or below. It's a $1 million question. It's either going to look like this, okay, or it's going to look like this, because the asymptotes act like gravity. So which one is it, above or below? Below. What? I heard both. How about this? Let's say it did live below. What would we have already found if it did live below? We would have found an X-Intercept, right? There would already be an X-Intercept that's plotted that shows that it lives below. Did we find an X-Intercept to the left of -5? No, the only X-Intercept we found was at -1. Therefore, by default, it can't live below because there's not another X-Intercept, so guess what? It has to live above. So sometimes you have to look at what's not there to help you decide what is there, right? And that's what the graph looks like. Pretty cool, right? It's a pretty nice looking graph. Now, I'm not even going to bother going to my calculator and typing it in because I know that the calculator's graph is going to be vastly inferior to ours. And I don't want to make the calculator feel bad. Okay? All of our relevant points are labeled. Okay? So from here, we can determine intervals of increasing and decreasing and all that good stuff. All right, let's go ahead and do that. What are the intervals where this function is increasing? F is increasing on what interval? Yeah, -infinity up to -5, union -5 up to positive infinity. There's a hole. Do we have to step over the hole? If it's not in the domain, we do. 2, union, and then 2 to infinity. This function is monotonic increasing over its domain, or strictly increasing over its domain. All right, the last thing we're going to do here, there's no local extrema. We want to find the range of the function. We get the domain from the equation, but we kind of need the graph for the range. What y values does this take on? We'll say it's the set of all y's such that y does not equal what? Yeah, where what? Man. It's all right. Where was the asymptote? it was at 2/3. This function does not touch or cross its horizontal asymptote, so that y value is out of the range. Any other y values that we don't reach or get? There's one more. 2/7. Very good. 2/7 is the y value of the hole. Now you got to be careful. If you have a hole or something like that, sometimes you could pick it up in another place. Like if this branch had lived below the horizontal asymptote on the left, it would have passed through 2/7 on this side. But we don't pick up that y value anywhere else. So those are the only two y values that are not in the domain. So you can list it like that, or you could do it in interval notation, right? Negative infinity up to 2/7, union 2/7 to 2/3, union 2/3 to infinity. Okay? So there's the range. Beautiful. Anything else you want to say about this function before we say hasta la vista? Or hasta la never? You think you'll ever come back and revisit this guy? Probably not. 30 years from now, you'll be going through your Notability PDF backup file on your computer. You're like, oh, can I delete this? You're going, what do we do on Sneakers Day? Oh, yeah, I remember that guy. Right? Delete. Okay? All right, so we're done. Do you see how enjoyable that was? That was like downright pleasant. Okay? Do we have time for another one? I think we do. Yeah, we do. Yeah, we do. 6 minutes. Okay. Let's do one of these piecewise fellas down here. Which piecewise fella do you want to look at? All right, so let's do D. Yeah, cool. All right, let's do it. Yeah. These are easy. These are easier than the other ones, right? Okay, let's look at the domain. What's the domain of this function? First thing you do, remember, for a piecewise function is you look at the pieces themselves. Do they have any built-in discontinuities, like holes or VAs? We got a x squared function, which is a parabola. There's no discontinuities. We have a line on the bottom. There's no discontinuities. And we have a dot, 0, 2. So they don't have any built-in discontinuities. What do I mean by built-in discontinuities? It would be like one, if we had like 1 over x, then we would say, oh, x can't be 0. All right? So the next thing we do is we look to see where it's defined. It's defined to the left of -1, to the right of +1, and at 0? So it's just in between those? Yeah. So the domain of this function is the set of all x such that x is less than -1, x equals 0, and x is greater than 1. All right? How would you even list that in interval notation? That would be like this: negative infinity to -1, bracket or parenthesis? Parenthesis, right? Union 0? Bless you. So that's how we do it. We put brackets around it if it's just a single point, and then union parenthesis 1 to infinity. So this is an interesting dude, right? All right, so remember, to sketch a piecewise function, now that we have the domain, is we go to the x values where it changes. And we are interested in the limits from the left and right. In this case, what is the limit from the left of -1? What is the limit from the left of -1? What do you get when you plug a -1 in to the top piece? You get 0, right? So that's the limit from the left. Is it going to be plotted with an open circle or a solid dot? Open circle, okay? And now I need to know what that function looks like. It would be x squared minus 1. So that would be a parabola that would be coming down like that, and it would eventually, cross right there through the 0, -1. But I'm not sketching it any further than -1 down there. So that's that piece. 0, 2, that's easy. 0, 2 looks like this. And then the function to the right of 1, what's the limit from the right of 1? What do I get when I plug a 1 in there? Careful. I get -3 minus 3, which is, -6. That's way down here. And is it open or closed? Open. And now to the right of there, it's the slope of -3. So I'm just going to go down like that. There's the graph. Piecewise functions are a little bit different than rational functions. We don't necessarily collect all the information first. We actually sketch it, and then we can get the information. It's a little bit easier that way. Does this function have any symmetry? Sorry. No symmetry. You could tell. Let's go ahead and find the range, and we'll call it a day. The range. What is the range of this function? We'll do it in interval notation. We come from the bottom, which is -infinity, and we cruise up to what y value? I'll highlight it as we go. We're coming from -infinity, and we get closer and closer to -6 with a parenthesis. Union, what's the next y value we start at? -0? 0, right? With a parenthesis or a bracket. It's an open circle, right? 0. And what about at 0, 2? Do we need to make any special allowance for that? No, because it's included. Right, it's included in that piece there. So then we just cruise to infinity. There you go. There's the range. All right? So we'll stop right there. We probably will not finish the rest of this. So tomorrow we will start the next section, okay? But this is enough to get you going in your worksheet and to finish your worksheet, right? Which, remember, the key to the worksheet is posted online. Okay, so we're finally done with 2.3. Enjoy the rest of your sneaky sneaker day. May your other teachers not be so annoying with their